we have one order of business today. So far in block 2, you've seen MPDAs, that's our machine for this block. You've seen context-free grammars, that's our set builder, set of string builder for this block, analogous to DFAs and NFAs on the one hand and regular expressions on the other. We've seen what can be done with context-free languages. Any set accepted by an MPDA is context-free. Any set generated by a context-free grammar is context-free. We've seen how to say yes to the question of, is this set context-free? Today is our one day where we're going to see the other half. How to show a set isn't context-free. And before we get started, I want to comment, to not be context-free, you have 2 avenues of proving that. 1, somehow prove that no NPDA can accept this set. That is just not even, that's a non-starter. MPDAs are way too complicated to come up with a good way of telling, given the properties of an MPDA, whether it can accept a given set of strings or not. Grammars are a different situation. We're going to take context-free grammars as our kind of grabbing on spot for a pumping lemma for context-free languages. This is going to be a property that context-free languages do have, and if we can show another set of strings doesn't have the property, it can't be context-free, is exactly like, in terms of how it's used, exactly like the pumping lemma from block 1. Big warning, there's a lot of similarities to this pumping lemma, including the name. Be very, very careful. I'm not going to ask about the regular set pumping lemma on exam 2, and I didn't ask about the context-free set pumping lemma on exam 1. Whatever background you got from how the pumping lemma kind of worked logically, you can carry forward, but please don't confuse the two. They're different in very substantial ways, and I'll try and point those out. But there are a lot of common themes, okay? The first difference is we're going to prove the pumping lemma for context-free languages. Our goal today is to understand why it's true, get a clean statement of it, and maybe do one proof that a language isn't context-free. Again, that no MPDA can accept it, that no context-free grammar can generate it. What I want to do is warm us up by looking at a grammar that you may or may not recognize, depends how much of the problem set you've gotten through. This is a grammar for non-squares. I mentioned in class the other day that the set of squares, any string times itself, is not context-free, and we'll be able to prove that by today. And the set of non-squares is, the complement is, which is kind of interesting, okay? This is a grammar for the set of all non-squares. If you read through the problems already, you might remember what some of these things mean. I'm not requiring you to memorize this grammar. All I want to do is do a derivation with a derivation tree in this grammar and make an observation. This is akin to what we did in the first block, where we put a DFA up, ran a long string through it, and noticed a loop. That loop was the key to figuring out how to do the pumping lemma. Now it's going to be on the grammar side. I'm just going to start, just to review, like we're a week or two into, maybe 1 week into context-free grammars now, short block. I'm going to pick a production for S, right? It's context-free. I can choose to derive on anything I want. I'll change the B to XBX. Maybe I'll change the next B to XBX. I'll change the A to XAX. I don't know. I'll change the other A to XAX. I don't know, whatever. Let me just fill in now some terminals. So this is kind of meant to look like how you would typically do a derivation tree, say with a grammar in Chomsky normal form. Let's do all of the splits first and then the change to a terminal at the end. By the way, is this grammar in Chomsky normal form? No, why not? XB. Yeah, the XBX and XAX are the wrong length. With a couple more productions and a couple more non-terminals, this could be. It doesn't make any difference. I just want to show you what happens in a derivation tree. The key point about a grammar that we need is that there's only a finite number of non-terminals, in this case 4, S, A, B, and X. Pay attention to the non-terminals. What I want you to do is look at this tree and look at paths from the S down to a terminal. You should notice something, and this is a ridiculous thing to notice. Any long enough path, this is the pigeonhole principle again, just like it was in block 1, any long enough path from the S at the bottom out to the end has to repeat a non-terminal somewhere. In this case, there's non-terminals repeated all over the place. Look at the left branch, S, then B, then B, then B. The fact that B gets repeated, that's the easy thing we're going to grab onto to understand the pumping lemma, okay? So let me just kind of mark these. So here's the thing to observe. If you ever have a string with a derivation tree that some path from root down to end repeats a non-terminal, you can do this. What can you do? This is the graphical introduction to the pumping lemma. I've color-coded things a little bit. I sort of chose the first B was blue, moving up the tree, I suppose, from root to branch. I've color-coded the first B I hit and everything under it blue. And then inside of that, the second B I've chosen everything under it red. Just to let you see a breakdown of this tree. Here's my question to you. What does the fact that non-terminal B appearing twice along that chain, the blue one and the red one, pay attention to the blue one and the red one, does this suggest a way of modifying this derivation tree to get a different string? That's what we did in the pumping lemma for regular sets, right? We had a long path through the DFA, there was a loop. That loop meant that we could do the loop as many times as we wanted to, and we'd still get the string accepted. Same thing here. This string can be generated, A, B, 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 A, B, whatever it is. This string can be generated. Think of pulling it apart into the red part, the blue part, the green part. Can anyone tell me how to modify this? Yes?
Do we repeat the blue part inside?
Yeah. This blue part's like our loop, right? This is a B that leads to another B. The B to B link, whatever happened, it could be a bunch of steps in between, but there's a B somewhere in the tree and a B somewhere higher up in the tree. The blue bit I could repeat, or I could take it out. So here's the idea. This string, blue, red, blue, the green doesn't change. Okay, by the way, there could be some green on the left too. I just chose a bad spot. Okay? Notice that the blue B, doesn't matter what's around it, that B can turn to anything a B is allowed to turn into. One thing it's allowed to turn into is the red thing. I could take out the blue layer and get this string. Immediately, there's a derivation tree for this string. That's the 0. That's the pump down. That's the I equals 0 case. My original string's the I equals 1 case. I've repeated that blue part once. I could also say, take that first blue B, do that layer again, and then turn it to the red B thing. So the red part is in the inside. The green part doesn't change. This blue part, I could repeat as many times as I like. There's twice, 3 times, 4 times, 5 times. The key thing is, because it's a B leading to a B, I can choose to do that blue part as many times as I like, and then finish it by doing the red part. Does that make sense? Yes?
Is there not an inside loop again with the B going to X, B, X? Can we not say you can go to like the terminal B?
So the way we're going to deal with the pumping lemma, that's good. There are lots of choices. There were lots of pairs of like, I could have taken this A and that A. I could have taken this A and the top A. I could have taken any of the 2 non-terminal appearing on a path from root to bottom. I'm only going to choose one of them. Yeah.
But could we do that B go like in the red? There's
Yes.
a B that goes into a B.
Yes.
Can we have?
Oh yeah, we could change that to a blue B as well, yeah.
Okay,
Yep.
so it could go straight to a terminal.
Oh yes, yeah. So, and these are your productions, right? You're allowed to apply any of these anytime you want. Now, this is a very specific case where there's lots of A's and lots of B's. All you need is a path from root down to the end that repeats one non-terminal twice. Here there happen to be a bunch. Choose any 2 you like, right? Moving up to the first one, creates a little subtree. All that blue and red grows from a single B. Inside that little subtree, there's another B, and all the red stuff grows from the second B. Those are both things you could do with the B, and you can do the blue one as many times as you want. Okay? It would be your choice which B's to choose to pump on. So for instance, I mean, here's a different pumping, right? Here's pumping on one of the A's and then the next day. Any 2 of the same non-terminal on a path, it's a tree, there's a unique path from the root to any spot in the end. As long as you repeat a non-terminal twice, you can do this breakdown. Okay, there it is with the blue A and the red A, right? I could take the blue part out. That is a derivation that follows the same productions, just in a different way. I could put it in twice, I could put it in 3 times, put it in 4 times. Now, thinking ahead to how this is going to look, it's unfortunately going to be a little bit more complicated and very different than the pumping lemma for regular sets. There will be a green part at the start that doesn't change. There will be a left-hand part that gets pumped up, and simultaneously a right-hand part that gets pumped up, and a part in the middle that doesn't change. So the pumping happens in a different spot. Given a long string generated by your grammar, there's an infinite sequence of strings that also can be generated by this grammar. That's the similarity. All our goal is, before I take this picture down, I want to make sure you're clear about it. If you see two of the same non-terminal, the blue, put it back to the original, the blue and the red, I could repeat that blue layer as many times as I want, and whenever I choose to, I could apply the red part to finish it off. Yes?
Can you do this if it's like a cycle of more than one non-terminal? Like if like A went to XBX and B went to XAX, then like you would have like a group of like an A and a B that you could repeat.
Well, we're keeping it simple. Any repeating thing in a tree you could work with. We're doing the simplest thing possible. Here's the key thing. Now think back to the pumping lemma in block 1. We want to figure out a way to guarantee that such a repeat happens. Guaranteeing that some more complicated repeat happens, that there's like 3 A's, you could choose which one, or that there's different, too much. We're just going to ask ourselves, how can we guarantee, and that's going to be the pumping lemma, how long does the string have to be to guarantee there's some path that repeats a non-terminal? If the non-terminal repeats, that's the half you're seeing right now. Okay, again, think if the tree is broken apart. That blue thing, that blue production, A goes to XAX, could be done as many times as you want. And then whenever you decide to, you can apply the red production to finish it off. But this layering is really important. There's some green stuff that doesn't change in principle, some blue stuff that does, some red stuff that doesn't, some blue stuff that does. This pumping up is happening simultaneously on both sides of the middle bit. And you'll see that in the formula once we put it down. There could also be some stuff that doesn't change at the right. This is the picture that we're working on, and it's a little more complicated than the loop in an NFA or DFA, I guess DFA. If there's any question about how this production, how this derivation tree argument works, this is what we're going to be trying to put in symbols. So the first step is to make sure this is clear. Again, an A could split as the blue one does, or it could turn into what the red one does. Any A at any time could do this. Along that chain, that allows me to repeat the blue thing as many times as I want, which gives me another A and another A and another A and another A, right? And then whenever I want to finish it off, I put the red thing in the middle, and I've got a complete derivation tree. Okay, without the red, it's not complete, right? There's an A that hasn't produced anything yet. So you do the blue as many times as you want, then once you put in the red one, then you've got a complete derivation tree. Yes.
For a question of using the pumping lemma in here,
Yep.
do we have to come up with a string or with the derivation tree ourselves and then pump it up?
You will have to come up with the string. The universe will give you the derivation tree and this split into 5 symbols, and it's going to be some case checking.
Okay, so with the question, we will get the derivation tree.
No. You will get the grammar. Well, I mean, you won't even get the grammar, sorry. What we're going to try and turn this into is a statement about context-free languages. You give me any context-free language, I need to turn this into a statement that says, if your string's long enough, there's a way to split it up and pump it. And we want to take the grammar out of the equation, just like the way we took the DFA out of the equation for the original pumping lemma. So first step is to see how to understand pumping in terms of a derivation tree. I'm going to close this and not bring it back up again.
Does it need to be like an A to an A, or can it be a B then another?
Oh yeah, they don't have to be consecutive, for sure. They don't have to be consecutive. I mean, for instance,
Like that works.
that would be another valid pumping situation. Because there's so many chains with repeated letters, there's lots of ways that you could pump this one up. You could have a more complicated blue part and a smaller red part. It could be anything. The main thing is there's the outer stuff, which is green, doesn't change. There's the middle layer, which you're going to repeat. In this case, it's going to be 2 symbols on each side. And then there's the red part that doesn't change either. It's going to be constant, changing simultaneously, constant. There's kind of 5 pieces here. I will color code the symbols the same way. So keep it in your head. There's the green stuff that doesn't change, the blue stuff on each side of the red that does, and then maybe some more green stuff that doesn't change. That's your picture. If you want a clear picture, maybe we'll pump on here, and then you'll see it. When you pump up, notice, I just want you to have one last thing to notice. The red and the green don't change, right? And the 2 bits of the blue before and after change synchronously, right? They change in sync with each other simultaneously. Okay, and this is an example where it's further down. But all you need is the same non-terminal repeated twice on some chain from bottom to top. That is step 1. Again, since it's repeated, when you see the B, you could do the blue thing, which gives you another B, as many times as you want, and finally you can do the red thing to get rid of it. That's the basic idea. You could bump on the A's, the B's, the S's. Any repeated non-terminal along one of these paths from the root of the tree down to a branch, as long as you see a repeated non-terminal, this is what happens. You're going to see this expressed in symbols. You can kind of guess. I'll tell you how it's going to go. It's going to be U, V to the I, that's the left-hand stuff in blue, W, X to the I, Y. It's going to be 5 letters. So keep this picture, by the way. I will give you a handout with everything that comes up on the slides and some pictures on the back to remind you this is where everything comes from today. All right? All right, so here is the main question. What we need is to figure out how long a string has to be to guarantee that that happens, that there's some way of pumping up or down the string. Okay, so how's that going to go? First remark, if we're given any grammar, we can put it in Chomsky normal form. Okay? If you recall when I first introduced Chomsky normal form, the idea was Chomsky normal form puts the size of the tree and the length of the string in direct correlation. So if we think of what a Chomsky normal form tree looks like, it starts with an S. You do all the non-terminal productions, which are splits. There's binary split, 1 non-terminal into 2. At the very end, you just fill in all the terminal productions. Until you get to the very top of the tree, it's all a binary tree. So here's my silly question. Think about how deep a tree is versus how long of a string it could possibly produce. A derivation tree of depth 0 in Chomsky normal form will have 0 depth, just a root, which will produce some terminal. When you have depth 0, you get a single symbol, 2 to the 0. When you have depth 1 non-terminal production and changing to terminals, you'll get maximum string of length 2 to 1. This is a complete binary tree of depth 1. I hope this is obvious, right? The idea is to make this as obvious as possible. If you have a binary tree of depth 2, you're going to get 2 squared. This is the part we need. Chomsky normal form derivation tree, if the depth is D, it's a binary tree until the very end, it can produce a string of length at most 2 to the D. If the depth is 3, maybe some of these didn't happen. It doesn't have to be a complete binary tree of depth 3. But the longest you could possibly get is 2 cubed. Okay? In general, if the depth is D, the length of the string is at most 2 to the D. Easy enough? We've got a stupid mnemonic for this one. Sorry, it's not quite as good, but at least you know what that is. Everyone knows what kazoo is, right? No? Really?
What the hell is that?
It's a ridiculous instrument that you play as a kid. Who here has played a kazoo at some point? Okay, some of you have, not all of you. Well, take my word for it. It sounds ridiculous. Sorry, you have to ignore the VWXY just follows in alphabetic progression. It's AKZUI. Closest I can come to something real that is better than the one that you didn't know the name of for the first one.
Where are the O's?
Huh?
There are no O's.
Yeah, well, it's not perfect. I mean, the I part you remember from the pumping lemma before. There's always some pumping, right? The AKZU is the key part to remember. And there's 5 parts. You kind of have to remember that as well. Kazoo has 5 letters. I don't know, whatever. Not nonsense mnemonics. Let's phrase how we can conclude the pumping lemma and then strip away the language from, or sorry, strip away the grammar from it. So here we go. If we're given a context-free language, that's a set of strings. Okay? Context-free means there's some context-free grammar that generates it. So far, so good. That's the definition of context-free. We could put that context-free grammar into Chomsky normal form, right? Do remember that when you put a grammar in Chomsky normal form, you might not be able to generate the empty string anymore. The empty string is the shortest string you've got. It's not going to affect any of this. We're going to be talking about long strings for the pumping lemma, not caring the least bit about the empty string anyway. Okay? Here is the standard thing we said about Chomsky normal form. In a derivation from a grammar in Chomsky normal form, a string of length n We'll do 2n minus 1 productions. There will be n minus 1 productions that split your non-terminal. And you'll have n non-terminals, then you'll just have n terminal productions. I care about the first ones. If you've got a string of length n, you'll use n minus 1 binary splits in your tree. If you ignore the production of terminals, what you get for derivation tree is always a binary tree. Okay, now use the observation that we made. If G has T, I'm sorry I used the letter T, or I use N for something else. T non-terminals, like these are the variables. Here's our last question to be able to state the whole lemma. How long does a string have to be to guarantee that we get that repeated non-terminal? Well, you can think this through, right? If you've got T non-terminals, the biggest your tree could be without giving you a repeated non-terminal would be a complete tree of depth T minus 1. Notice a tree of depth 0 still has 1 non-terminal in it, and a tree of depth 1 has 2 non-terminals. Okay? So the biggest your tree could possibly be to not give you a chain of length T would be a string of size 2 to the T minus 1. Yes?
How do we know that the non-terminal goes to the exact same non-terminal and not like a to the x and then x to the a again? Like, why does the repeat happens directly?
Oh, it doesn't have to, there could be stuff in between, absolutely. So I made a very small derivation tree and it happened they were consecutive. Later I did one where they weren't. They definitely don't have to be consecutive. Somewhere along that chain from S out to the end, the same non-terminal appears twice. I don't care how far apart they are. Absolutely, they don't have to be consecutive, 100%. So sorry about the symbols here, but if the depth were T minus 1 for your tree, you could generate at most a string of length 2 to the T minus 1. That's the thing we saw about binary trees, right? So what we're going to do is say, if T is your number of non-terminals, if K is 2 to the T, that gives you a target length bigger than 2 to the T minus 1. Any string more than K symbols long, the tree must have a non-terminal repeated twice along some chain. Okay? If your string is greater than length 2 to the T minus 1, your binary tree has to have depth greater than T minus 1, has depth at least T. There are T plus 1 non-terminals seen on that chain, and it has to repeat 1 once. There may be lots of repeats, I don't care. I want a condition that guarantees somewhere in the tree along a chain from the root out to the end, there's a repeated non-terminal. This happens to be, honestly, all this is going to go away. This is very specific to the grammar. But this is how the argument goes. If you walk back up that maximal chain, you'll see T plus 1 non-terminals, and therefore 1 must be repeated. This buys us into the picture we saw first. So we're working this one step at a time. First, see the picture for an explicit grammar, and see what you're looking for, a chain that repeats a non-terminal. We've now justified how to guarantee such a repeat, such a chain. If our grammar's in Chomsky normal form, which is necessary to tie lengths to depths, all I have to do is take a string 2 to the number of if I have 3 non-terminals, any string of length 8 will work. If I have 10 non-terminals, any string of length 10, 24 or more will work. But there is a length, a critical length k, that if you have a string longer than that in your set, will be able to get this pumping to work. Okay? Now I'm just going to color code. Sorry, it's all variables now. Remember the idea? There was this outer green tree. There was this first non-terminal in blue that generated the VWX. And then there was the red non-terminal, same one, that generates a W. In letters, and I've color coded to have you remember it, Z gets split into U, V, W, X, Y, 5 pieces. Remember which ones are going to change and which ones aren't when we pump.
V and X.
Yeah, the blue will change synchronously. You'll have to have the same power on both. The red and green will not. And a quick note, we can actually limit how long that string VWX is where the pumping occurs. We know how long our chain was. If my first non-terminal to the end is at most T steps, then the length of the string in the middle from the blue one can only be at most 2 to the T. All these details are going to wash out actually when we get the actual statement of the theorem, so you think through these carefully. But again, if you get a deep enough tree, you'll get a repeated non-terminal. That gives you the split. You actually can control the length of the middle bit. Just take your split to be as far to the top as you can. Then you'll guarantee that your pumping bit isn't too long. All this will be important in the final bit. Next quick note, at least one of V or X. So remember, the blue B in my example turned into some blue stuff, and some red stuff. There's at least one production applied between the first B and the second B. That will spit off at least one symbol to the left or right, maybe both. But the point is, V and W, at least one of them has to be non-empty.
V and X.
V and X, sorry. Of the two things they're going to pump, some pumping will be possible, right? Two things you know. The string of the blue and red together doesn't have to be too long. And there's at least one symbol in V or X. Because you can't have a symbol going to a single symbol. That's not Chomsky normal form. There has to be a split happening in a production. There has to be something on the left or right. Okay, it's possible V is empty, but then X is going to have to be non-empty. It's possible X is empty, then V has to be non-empty. The blue bits I could repeat as many times as I wanted to. I could repeat the blue bits, the V and X, as many times as I wanted to. The U, W, and Y, the green, red, and green stay the same. When I pump up, I'm just adding that middle layer as many times as I want. The V will get a power and the X will get a power. Yes?
Wait, I'm just confused. Shouldn't V and X be the same thing?
Oh, no, in my grammar I was testing with, it so happened it was spitting an A on the one side and an A on the other. Your production could spit off whatever on both sides. Don't let any details of the example mean too much to you. The distance between the two non-terminals can't be more than K, or can't be more than T, but they could be far apart, they could be consecutive.
But if one of them is empty, does that mean that pumping happens on one side only?
Yep, absolutely.
Why? I understand why I can be greater than 1. Why can it always be 0? Like you can just get rid of.
Remember in our example, there was that blue layer, and it was a B produced the blue and then the red inside. That original B I could have applied the red production to and gotten rid of the middle layer. Yep. So that blue layer I can repeat as many times as I want, including 0. That is the pumping lemma. I mean, that is not the pumping lemma. That is what we can argue to get the pumping lemma. I'd like to take what I've just explained. If there's any question about that, we should address it now. There's a context-free language, make a grammar out of it, put it in Chomsky normal form. As long as I get a long enough string, the Chomsky normal form tree will be binary. I can force there to be a repeated non-terminal. That's the thing we saw first. That splits your string into 5 pieces. The middle part's not too long, and there's at least one symbol in the blue bits, right? I can put any power I like on the V and the X. Landing spot number is like the climbing Everest, right? The first base camp was the picture. Second base camp is this. This has the full explanation of why the pumping lemma happens, along with the picture you saw first. The picture shows you the basic idea of how the pumping happens. This shows you how to guarantee it. Yes, Elise.
So, if V or X is empty, that basically means you're pumping all the way to the right or all the way to the left, right?
Well, you're pumping only symbols on one side will grow or shrink. That's right, and the other side will stay the same.
But that will only happen because we're in empty string. That will only.
Yeah, there's basically no non-terminals there at all. Yes.
That means that if we were, for instance, using
Yes.
Y.
Yeah, Greibach normal form is not going to work for us here because we really want the binary tree for this argument. Greibach is very controlled, but each split could be into multiple non-terminals. Plus there's a terminal popping off. It's not convenient for this, but yeah. Okay. Last bit is to take this full derivation of what we saw and remove all reference to the grammar. Okay, here we go. Given a context-free language A, I've gotten that far, haven't mentioned the grammar yet. There exists some context-free grammar G, don't want to mention that. In Chomsky normal form, don't want to mention that. Whose language is A? Don't want to mention that either. G has T non-terminals, don't want to mention that. Right? How long does the string have to be to guarantee a non-terminal depth at least T in this derivation tree? Don't want to mention that either. The maximal case dot such non-terminal will be a complete binary tree of depth T minus 1. That's talk about the tree. Don't want to talk about that. Right? The next thing that really matters in the statement is that there is some number K that tells me how long my strings have to be. Okay? The second bit that matters, given a context-free language, reasons, the reasons don't matter. There is a number k. Second bit that matters. It doesn't matter that it's 2 to the t. I can't matter that it's 2 to the t because I don't know what the grammar is. I'm trying to remove the grammar entirely. Remove the tree, remove the grammar, remove the chain, remove everything from this statement to make it a statement just about the strings in the language. Okay, I don't care what k was. The key thing is that any string of length at least k, something happens. Now what happens? The derivation tree must have a non-terminal of depth at least t. I don't want to say that. Talks about the tree and the grammar. Walking back up the tree, no, don't want to say that. From this non-terminal for t steps, we visit our t plus 1 non-terminals with repeat at least 1. Don't want to say that either. The repeated non-terminal tells us that, that's the next thing that matters. Talking just about the strings, given a context-free language, there's a number k. Okay, k's to the number of non-terminals. Not going to mention that. Any string of at least k symbols in length that's in, oh God. The string z is supposed to be in your context-free language A. Given a context-free language, there's some number k. Any string z in the set A of length at least k, it splits. It's like the pumping lemma before, the split is different. Okay, as we saw in our example, forget that. Because either pair of blah, 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 blah. The key thing is that middle bit is at most k symbols long, because the first of the two repeated non-terminals doesn't need to be too far from the end. It doesn't matter about that. V and X, one of them has to be non-empty, maybe both. And finally, this last bit, put any I you like for all I greater than 0. This string's also an A. This is the pumping lemma. There's the bits, erasing the bits that we didn't want to say because they talked about the tree or the context-free grammar. A, given a context-free language A. There's some number k, that's the k. Any z you choose that's long enough, any string of A that you choose is long enough, it splits into 5 pieces. The middle bit is at most k symbols long, and at least one of V and X is an empty. And the final bit, no matter what power you put on the V and the X, the new string is still in your set. Why the k exists is because of Chomsky normal form and the size of the string and the depth of the tree, right? You don't have to know that for the statement. The y, z splits is because of what you see in the derivation tree. But what happens is that z splits and you can pump up or down. You provide the A, the universe provides the k. You say, let k be given. The first 2 lines are almost identical for a contradiction proof, are almost identical to the pumping lemma in part 1. You will get to choose a z as long as it's long enough and in the set. The universe will tell you how to split that into 5 pieces, and you won't know. It's just u, v, w, x, and you only know 2 things. v, w, x isn't too long, and v and x aren't both empty. And then finally, u will get to choose a value I to pump it up or down. Okay? So how does this work for showing languages in context free? This will look very familiar except for the details. The structure is the same. You will suppose that A is context free for contradiction. The pumping lemma will give you a k such that all that happens. You will have, this is the hardest part, you will have to choose a string in A that's long. Whatever k was given to you, and you won't know it's just the letter k, you'll have to find a string of length k, at least k. The universe will give you back, whatever your string you provided was, there's some way of splitting it into 5 pieces. All you'll know, you won't know which part's the u, what part's the v, what's the w, what's the x, and what's the y. You will know that the middle part can't be longer than k symbols, and that the v and x aren't both empty. At least one of them is not empty. Otherwise, pumping wouldn't do anything. What you will do is, just like in the pumping lemma before, try and find an I that breaks that string out of the set. And then you've got your contradiction. If you have that contradiction, then you have proven your set's not context-free. These are long proofs, particularly because of this. In the pumping lemma, as we present it in block 1, you got to choose a window where the pumping occurred in your string. And you could often arrange that that window had all the same symbol. Not the case for the pumping lemma for context-free sets. We have no control where the pumping occurs. I make this long string, the pumping is going to occur, there's some split somewhere u, v, w, x, y, and I don't know how that split happens. You're going to inherently have to do some cases. Maybe the pumping occurs just in this string of a's at the start. Maybe it occurs between the a's and the b's. Maybe just in the b's. Maybe between the b's and the c's. You'll have to do cases of where the pumping might have occurred. But it's crucial that the window for the pumping is at least controlled in size. You'll only have to look at windows of a length at most k. But depending on what your string's formed of, there will be cases. What if the pumping's here? What if it's here? What if it's here? What's here? What you're going to have to prove is, no matter where the pumping occurs, there's a value of I you can choose to break this string out. You will not know the k. It'll just be a k. You will not know how the string splits. All you'll know is that where the pumping occurs is not too big and that v or x is not empty. Yes?
Can W be empty?
This is the statement that must be true, and this kind of gets at your question as well. The same thing could happen from a derivation tree in non-Chomsky normal form, and then some of these things actually could happen in that case. The pumping lemma allows W to be empty. The pumping lemma, in fact, allows U, W, and Y all to be empty, possibly. All it tells you that the B and the X can't be both empty. Yes?
So, but initially you say, because it's a binary split, it's like in the middle, there has to be, I mean, the Chomsky normal form, there has to be something in the middle, so how can W be empty?
I no longer in my pumping lemma have said Chomsky normal form. Right? I took that out. This is true about the language, regardless of what grammar you're using. So this is grammar agnostic. This would happen regardless of which grammar. You might be handed a grammar not in Chomsky normal form. We proved it using the fact that we can put our grammar in Chomsky normal form. But the statement we get is going to hold regardless of that. So even though in Chomsky normal form, we would be able to guarantee the W wasn't empty, here we're going to not bother with it. I mean, you could say, you would be allowed to say K is bigger. You'd be allowed to say maybe W has to be non-empty or something. This is the classical way you say the pumping lemma. The stuff that's not obvious from what's here, we're not going to bother insisting on. It just makes the pumping lemma more complicated. This is going to be a lot to absorb. Your goal for today, I mean, it's one day out of what, 24 in a 300 level CS class. This is the culmination of today. That is the pumping lemma. It's 5 steps, basically, 5 logical steps. Make sure you know them exactly. And it gives you a way to try and show a set's not context-free. And this is a heavier lift than showing a set's not regular, right? Regular sets are fairly simple, honestly. Showing a set's not regular is not too hard. It's the pumping lemma. This pumping lemma shows that not even an NPDA and not even a context-free grammar can generate it. To show a set's more complicated than that is a heavier lift automatically, right? You've got a broader class of sets of strings, a broader class of languages. That your language isn't context-free is a bigger thing to show. Okay, so you get a slightly heavier pumping lemma. By the way, last pumping lemma of the class. The proofy stuff in block 5, there's nothing resembling a pumping lemma. Turing machines are way too powerful to get a nice statement like this about what's called recursively enumerable and what isn't. The game's going to totally change. This is your last pumping lemma of the course. You can bootstrap a little bit. It looks a bit like your other pumping lemma. This is a heavier pumping lemma for a more complicated kind of set, but it's doable, right? What I'd like to do is get to a poster child for a non-context-free set. You've worked enough with maybe grammars, but certainly NPDAs. You can imagine it would be difficult to design an NPDA that checked that a string of A's and B's had the form A to the N, B to the N, A to the N. Concern? Yes.
I had a question.
Oh, previously. Oh, yes. Okay, yes.
For the red,
Yes.
what do you mean by like we can over
You have no control.
like for the regular sets pumping?
We could say, choose this window for the pumping to occur.
For the example of A to the N, B to the N, we can say like.
I want it in the A's. No such control now.
So how does it work for?
Well, we'll have to see. Yeah, so you'll almost always have cases in a pumping lemma now. So your first pumping lemma in that sense was easier. So Here's our poster child. We will see that this set can't be context-free. And again, why? Intuitively, you could see why you think it might not be context-free. An MPDA could read in the A's and push them on the stack. It could check the B's against that. A to the N, B to the N is not a problem. But after you check the A's and the B's, your stack's empty. There's nothing left to refer to check whether the A's, the third check, right? The number of B's equal the number of A's, good for an MPDA. But you've exhausted your stack by that point. It doesn't seem like it's possible to then check that the A's afterwards have the same number as the first two. That stack can get you out of the A to the N, B to the N being context-free, but the third N that also has to match two comparisons, you'll use up your stack before you get to the last A's. Now, that's just the intuition why you might think this set isn't context-free. That doesn't prove that we just aren't very smart with our NPDAs, and there was something more clever to do with our stack to make this set be accepted. You might also say, well, it seems difficult to make it out of a context-free grammar. It is. You could kind of see a B spitting off equal numbers of A's on both sides. But then how do you expand that B and keep it at the same number as the A's? There's no way to do it with a grammar either, context-free grammar. This set is not context-free. We can argue that an NPDA seems not to have the power to accept it. We can argue intuitively that a grammar doesn't seem to be able to generate this set. But to prove that there's no NPDA and no context-free grammar that accept or generate this set respectively, we need a proof. That's what we're going to do. So, call this set A if you like. Give your set a name just to do the reference. 5-step proof in some sense. The first two are boilerplate. Proof that's not context-free. Proof. In one screenful, if I can fit this without being too messy, we will prove that there's no way for an MPDA to accept this, no way for a context-free grammar to generate it. The proof is by contradiction. Suppose it were context-free, right? Then, this is the A kazoo. The pumping lemma says there is some k greater than or equal to 1. And reference with the ... right? That says a whole bunch, but the main thing is a k. A, k. Those are the first two lines every time. You provide the set A, suppose it's context-free. Pumping lemma universe provides a k. You know what the k is. It's going to stay k the whole proof. I can write the star of the next step, take z equals, and then you have to go figure out what string you want. The choice process for this string kind of has only two things. One, it has to be in the set, so it has to be in the form A to the N, B to the N, A to the N, right? It has to have length at least k. What's the easiest string you could write down, and you hope it works, easiest string you could write down that's going to be in the set and length at least k? Yeah, that is in the set A. I'm not going to make a long check of it. N equals k. Whatever k was, if k was 1,000, it's A to the 1,000, B to 1,000, A to 1,000. That's definitely in your set. And you should note that the length of z is 3k, which is certainly greater than or equal to k. That's what you needed. A, you're given the k. You provide the z. All you need to know is that it's in the set and long enough. Here's the tricky part. The pumping lemma says z must split as u, v, w, x, y. And the two things that you know is the length of v, w, x, the middle part, is at most k, and that the v and x are both empty. And that's useful. Actually, let me highlight this. By choosing your string to be KAs, then KBs, then KAs, the window you don't get to choose. The window is going to be somewhere in your string. But if you got KAs in a row, then KBs, then KAs, and your window for pumping is at most k units wide, there's only 5 cases. It stays within the first A's. It straddles the A's and the B's. It stays in the B's. It straddles the A's and the B's again, or it's all in the A's. There's actually 5 cases unavoidable. You don't know where the pumping happens for this pumping lemma. If I'd given you a weaker pumping lemma in block 1, you wouldn't know then either, but I think it's unnecessarily painful. Yes?
Can we not say that there has to be pumping happening in B's or in A's?
It turns out that we're going to have to argue for all 5 cases. If the pumping was here, there's an I can choose that breaks me out of the set. So there's going to be 5 different arguments.
It has to be true in all 5, right?
You need to contradict all 5 cases. Because the universe gets to choose the split, gets to choose where the pumping occurs and how that gets split up VWX. This is the one thing that's more complicated in this pumping lemma argument than before. You do not get to choose where the pumping occurs. If I wanted to show the set wasn't regular, I'd say take a to the k, b to the k, a to the k, and pump on the first a's. Done. New pumping lemma, more complicated type of set, you don't control where the pumping occurs. Yeah, Ryan.
Why does it have to be true for all? If there's one that breaks it, isn't that?
So there's going to be 5 cases where the pumping occurs. And in each case, you'll have to find an I that breaks it.
But in order for it to break, it only has to be true at one of those?
For the first case, you'll have to find an I that breaks this string out. Pump it up or down to move it out of the set. In the second case of the pumping, you have to find an I that moves up or down. Yes.
So I guess a follow-up question.
Yes.
If you check one case and you find one that breaks it, you have to check the other cases?
Yep. That 5-way split, the universe determines this. You don't know where it occurs. It's possible if you show a contradiction in case 1 that the universe chose case 3 and it works there. And we'll see this actually later. It's possible if you checked it for case 1, 2, 3, and 4, the universe chose case 5 where it does work. You need to show that there's no way, no matter where the pumping occurs, there's no way in any case for the pumping to actually succeed. So for each case, you're going to have to find an I that breaks this string out of the set. The good news is once you actually get into this example, I mean, by the way, this will fit on this page. Once you see how this goes, you will understand how this works. Just note that there are cases, okay? So here is your thing. Where is this string VWX? The answer is you don't know. But you do know this is the window for the pumping. You got to choose it in block 1. This is block 2, 1 block harder. You're going to have to handle wherever that pumping occurs. The only changes to my string occur in the VWX part. But remember, what was the point about your set? The point is that this, and this, the powers of A in the beginning, the powers of B in the middle, and the powers of A at the end have to all be the same. How would this argument go? Suppose that VWX is entirely in the first A's. It's a lot like the old pumping lemma now. It's all in the A's. When I pump up or down, what's the only thing that's going to change in my string? The first A's. Not the B's, and not the other A's. Pump any I other than 1. Take maybe I equals 0. You get to choose the I. The final choice is yours. If you take I equals 0, my Z will become A to the, I originally had K A's. V, W, and X are all A's. I've removed the length of V A's and the length of X A's. I've removed the V and the X from the string. And those are all A's. I've taken away length of V A's and length of X A's. I've still got KB's and I've still got AK's. It's obvious that's not in A. Why? Crucially, why? The number of A's I took away is length of V plus length of X. They can't both be empty. That's definitely not K, right? This power is not that power. So if the pumping occurs in the A's, I can increase or decrease any I except for 1 works. I equals 0, decrease the number of A's, doesn't match. I equals 2 or higher, increase the number of A's, doesn't match. Either way, case 1, the pumping occurring in that first block of A's, can't work. Ryan.
Couldn't you just say that pumping in the 5 windows is going to result in one window not also being pumped, which means that...
Yeah, if you're careful, if it were me, I might be happier saying, I'd want to see you reason it out for at least 2 types of windows, right? If you did this one, right, you got a contradiction if the pumping occurs in the first A's. You know, you still get a contradiction for the all B's, same idea. You can pump the B's without the A's changing, right? And you can pump the last A's the same way. The argument similarly for those other 2 pure blocks, all B's and all A's. Be a little bit careful. It's probably worth mentioning this second case. Suppose the window occurs somewhere in between, right? You still have to treat it. There are initial remarks. Your string has A's, then B's, then A's. The V can't straddle the A's and the B's. If the V involved both A's and B's, then I equals 2 would have an AB, and then a bunch of B's and then a bunch of A's, not even the right shape anymore. Ditto, the X can't have both A's and B's in it. I mean, write this out more carefully. You'll still see it argued out in detail in the problem set. The things that change can't involve both A's and B's, because you could take I equals 2 and repeat those and not even get the same shape, right? The only reasonable place the pumping might occur is the W is somewhere between the A's and B's. The V is all A's, and the X is all B's. Okay? How would the argument go at that point? The V has to lie on the A side, the first A's. The X has to lie on the B side, the second range of B's. If I take I equals 0, what happens? Well, I don't know. One of those is non-empty. Reduce the number of A's or the number of B's, or possibly both. What hasn't changed, and this was Ryan's comment from the start, what hasn't changed is the number of A's at the end, which I haven't even touched. So there are really two essential arguments. What happens if you're strictly in the first A's, or the second B's, or the third A's? Or what happens if you straddle? All 5 cases you can get a contradiction. And therefore, there's no way for the universe to eke its way into the pumping lemma working. The conclusion is the pumping lemma is contradicted. No matter which spot the pumping occurred, and there's so many choices the universe gets to make. Where does the pumping occur? How long was it? You need to be able to argue no matter where that pumping occurs, I can choose an I to make the new string not in the set. So A is not context-free.
But can I not simplify the argument and say that since the pumping is happening between the A's and the B's, that there will be pumping that will increase the local number of elements in here, or
Yeah.
symbols in here, but it won't affect the last A's.
As long as you say it carefully, that's valid, yeah.
Okay,
I'm
so
giving you a slightly more detailed argument to make sure you're careful about it, but yeah.
I don't need to say that V can only either be A's
Yeah.
or B's or both.
The reason B has to be all A's and X has to be all B's is fairly easy.
Okay.
But it would be okay if you phrase it carefully. If the pumping occurs within the first block of A's and B's, pumping down will reduce at least one of the number of A's or number of B's and possibly mess up the order. And that won't match the number of A's at the end. And then I wouldn't mind at all you saying that it happening between the B's and the A's is the same argument, more or less. Yes.
Maybe, I don't know if this is what Yaya was saying, but could you do all of them by just saying like a range of length? It's not possible for it to straddle
All 3.
of length K, which means any pumping changes the length of one part of it, which means that like necessarily.
As long as you say it carefully, this was Ryan's point too, as long as you say it carefully that the pumping occurring anywhere in the first A's and B's does not affect the final run of A's, and I equals 0 will reduce the number of A's and or the number of B's, 2 cases. There's really only essentially 2 cases anyway, the pure and the non-pure. There are lots of ways you could finish, but the main point is, this is the point that was asked originally, we need to know that no matter where the pumping occurs, I can get a string that should be in the set but isn't. So you can look at that a lot more carefully. As long as you say it carefully, Ryan's argument, Yaya's argument, these can be made as long as you say it carefully, exactly what happens when you pump up or down to I equals 0, I equals 2, say. Yeah.
So it seems to me that if this was like a single symbol alphabet,
Yes.
then BWX would all be the same symbol.
Yes.
And so the thing it feels like it's the same thing as ultimate periodicity.
In the case of a single symbol alphabet, it's pretty similar to ultimate
Does that
periodicity.
mean that all of the non-regular languages, like unary non-regular languages we looked at that are like the strings of length prime or
Yeah.
to the n are also not context free because of the same.
Yeah. Yep. Absolutely.
If it wasn't,
Exactly. Yeah.
Isn't it true that any regular set is context-free?
Yes. Finite sets simplest, regular sets next simple, context-free sets next simple. Context-free is a different world than regular, but for single symbol alphabets, things collapse a little bit. That's kind of long, but that's a start. I want to make sure you realize the pumping lemma does work for context-free sets. And this gets into the case question. It's why you have to show all the cases where the pumping occurs, you get a contradiction. How would the proof look if we tried, this is going to be a non-example of the pumping lemma. A to the n, B to the n, you've seen a context-free grammar for it, and you've seen an MPDA for it. This is definitely a context-free set of strings. You could push the A's onto the stack, you could pop off for the B's and check if they were equal. You could have a non-terminal that spit off A's and B's simultaneously and have it go away. This is context-free. Make sure you realize it's worth talking about a little bit. What happens when these arguments fail? Well, you might call that set A. Suppose A is context-free. Pumping lemma gives us a K. ... You need to choose a Z. Again, your choice of Z is not very interesting. It needs to be of length at least K. Because the windows you're looking at are K symbols long, you probably want to use A to the K, B to the K. That's in the set A. And the length of Z is 2K, which is definitely greater than or equal to K. So the pumping lemma applies. The pumping lemma splits my Z as U, V, W, X, Y. And again, the two key things, length of VWX is at most K, and V and X not both empty. Where could VWX be? There are three cases. I'm going to do the cases this time. There are three cases where the pumping might occur. Okay? It could be in the A's. It could be in the B's. It could be between the A's and the B's. Straddling. Now, if the VWX is in the A's, you could take I equals 0, change the number of A's, not change the number of B's, get a contradiction. If it occurred all in the B's, take I equals 0, you reduce the number of B's but not the number of A's, contradiction. Contradicting all of the cases except one is not good enough because your VWX could occur between the A's and the B's. I, as the universe, should be able to choose a VWX that works. And it's really not hard. You've got a bunch of A's, K of them, and then a bunch of B's, K of them. Can anyone find me a V, W, and X that I can pump up simultaneously the V and X and keep this in the set? Yeah, assuming K is at least 2, because I was a universal allowed to provide K. Let's make K at least 2, right? I could make my V as an A, my W as AB, and just the single B after it as my X. So everything before that is the U, and everything after that is the Y. What happens when I increase the power of V and X simultaneously?
They increase the same amount.
A and B stay the same size. This actually does work. You can't contradict the pumping lemma for a context-free set. The set is context-free. The pumping lemma does work. You cannot get a contradiction. The universe has a way to eke out success. Can't pump in the A's and the B's. We don't get to choose though. I, as the reader of this, don't get to choose the A's and the B's. Oh my God, 203, we're out of time. Let me get the problem set out. The only problems to look at are the top ones. First is a recap of the A to the N, B to the N, then A to the N, B to the N, A to the N, then a couple of other sets to think about the pumping lemma for. Wednesday is going to be, now that we know how to show sets are context-free, and now that show sets aren't context-free, at least a little bit today, talk about the pumping lemma some more and talk about, like, if you see a set, trying to determine if it's context-free or not.